Ja, herzlich willkommen und frohes neues Jahr für alle, die ich noch nicht gesehen habe oder die uns noch nicht gesehen haben. Sowohl hier im Raum, das ist jetzt eine überschaubare Menge, aber ich glaube, online sind noch ein paar mehr. Also herzlich willkommen zum ersten LIAG Seminar in diesem Jahr. Ich freue mich, dass Raphael sich dazu bereit erklärt hat, das LIAG Seminar zu geben. Und wir hatten schon einige EM-Vorträge in den letzten Jahren. Meistens waren die mit dem Desmex-Kontext verbunden, auch im Hauskolloquium sozusagen im größeren Rahmen zu Desmex. Dieses Jahr als LIAG-Seminar mal speziell zum Thema der drohnenbasierten semi-airborne Elektromagnetik mit sehr vielen Beispielen aus verschiedenen Kontexten, deswegen auch die ganzen verschiedenen Logos, die man jetzt sehen kann. Das ist also dieses Mal nicht nur Desmex, sondern auch diverse andere Projekte, um mal zu sehen, in welcher Bandbreite wir dieses Prinzip der semi-airborne Elektromagnetik, speziell jetzt mit Drohnen, weil das ist das, was uns am LIAG primär interessiert oder was wir vor allen Dingen vorantreiben, was man dabei tun kann. Und deswegen, Raphael hält auch den Vortrag, weil er sich quasi verantwortlich zeichnet für die Drohnen-EM am LIAG. Und genau, ich freue mich.
Danke, Mike. I hope slides are visible now. Perfect. So, welcome everybody to my talk about mineral and groundwater exploration with a UAV-based semi-airborne electromagnetic exploration system. And as you can see, there's a number of co-authors involved from the University of Münster and LIAG and formerly University of Cologne. Okay, I want to give you a short outline of the talk. So at first I want to explain again some details about the semi-airborne electromagnetic method, and in particular what is the advantage or maybe also disadvantage of using UAVs as carriers instead of helicopters. Then I will focus on a number of case studies, in particular recent inversion results of a HOPE survey performed in 2021 and 2023, and a number of other examples. And then I will continue with the discussion based on the experiences gained during all these cases and conclusions, and give you an outlook what will happen in the next months and years. What is the motivation? So Mike already mentioned we had the Desmex projects since 2015, and in the first 4 years till 2019, we focus only on helicopter-based semi-airborne electromagnetic surveying. So this is kind of a central part. And in the Desmex 2 projects, which ran until, yes, actually October last year, we extended the pool of methods to explore the subsurface, also by natural source helicopter borne surveys called AFMAC surveys and additional ground-based surveys. And one particular focus is to try to focus local investigation of specific targets with UAVs as carriers instead of helicopters. So on the regional scale, of course, helicopters can cover thousands of square kilometers, but on the local scale, UAVs flying slower and costing less money in operation are a valuable alternative. And this is what we are talking about in this talk. A short introduction to the method. So what we basically do is we inject currents with a transmitter into the subsurface. The currents flow through the subsurface and therefore flow through anomalies. And if we have anomalies, we have a change in the electric and magnetic fields. And if we measure the magnetic fields, we can, in the so-called inversion process, calculate our subsurface resistivity model. And the resistivity as a physical property is a characteristic for the subsurface. And of course, we also need to deal with effects caused by topography, or if we go to coastal regions, by water or saline water. And We reach penetration depths up to 1 kilometer, which is pretty good. And we can cover several square kilometers with a drone. Yeah, so this is basically the method. And what is the advantage over ground-based or airborne methods? So basically, if we have ground-based methods, we get very good data quality, but the data acquisition speed is quite slow, because we need to go from position to position, and we can measure maybe like 10 or 20 or 50 points per day. With airborne methods, on the other side, we can cover very large areas in a very short time, but we have not, the data quality is not too good, because we need to carry our transmitters with the airplane or with the helicopter. And that's why the source signal is usually not that strong compared to the ground-based methods. And kind of the compromise is we install sources at the ground with semi-airborne methods to get strong source signals, and we fly with our receivers with UAVs or helicopters in the air to have good data acquisition speed. So basically, we combine the pros of both methods and avoid the cons. Another advantage is that we do not need ground access for all our receiver locations if we fly the receiver with a UAV or with a helicopter. But of course, we need to say we will never reach the acquisition speed of pure airborne methods, and we will never reach the data quality of pure ground-based methods. It's a valid compromise. And particular comparison between helicopters or UAVs as carriers. So if we think about helicopters, we are able to cover very large areas on a regional scale with flight speeds of about 100 kilometers per hour. And we can use long rope lengths, so we do not have too much interference between the electromagnetic noise of the helicopter influencing our sensor. And we do, of course, we have weight limitations, but not like critical weight limitations. But on the other hand, we have high operational costs and logistical limitations, because we need access to airports in the region, we need pilots, we need permissions to fly with the helicopters. And on the other side, with UAVs, we can cover still large areas, but not as large as with helicopters. So we focus on the local scale, and we can acquire our data more densely because we have slower flight speed, so only a tenth of the helicopter flight speed. That means higher data coverage and higher resolution. But due to the weight limitations and kind of the geometry of the size of the UAV compared to the sensor, we are limited to shorter rod or rope lengths to kind of attach our sensor. So here comes kind of an issue of mutual noise interference from the UAV to the sensor into play. And overall, we have weight limitations of 25 kilograms of the UAVs. Otherwise, we would need to have permissions for another category of flying UAVs. And this is not worth the effort, let's say it like that. Big advantage is the operation costs are significantly lower. That allows us also to repeat surveys and extend our surveys to a longer time. And the logistics, I would say, is overall simpler in terms of permissions and things like that. Only issue is about transport of LiPo batteries if we think about international surveys. And in all the surveys I will present soon, we use two different transmitter systems. One system is the Metronics TXM transmitter, which we have at LIAG and also at the University of Münster, supplied with power by our LIAG generator. And for the surveys in Namibia and Spain, we used also a Zonge GGT10 transmitter. And this is how the grounding fields of our transmitter cables look. So we lay out the cable, and of course we need to connect the cable to the subsurface. And for this, we usually use installations of metal plates and cables to connect to the subsurface. With the receiver systems, we have a bit a few more modifications. So we have basically 3 different systems used for our surveys. The first system is a scalar magnetometer, an optically pumped magnetometer, the semi-airborne by geometrics, which is carried by the UAV with a 4-meter long ropes, or by 4 ropes, which are 4 meter long. And the second sensor is a vector magnetometer. So it measures all 3 components, X, Y, and Z of a magnetic field. And it can be either attached with a rod to the UAV, which is the kind of original system, or we have a modification, or the University of Münster has built a modification, putting the sensor and an inertial measurement unit in a bird to kind of extend the distance between UAV and sensor to reduce the system noise, and use a rope to connect the sensor with the UAV. So these are the 3 versions of systems we used for our surveys. And last thing about the, I don't want to go too much into detail, but for our raw data processing, we need to consider a few things in order to calculate our transfer functions, which we use for the inversion. We need to have always a good current recording of our transmitter current as a basis for all sensors. And the advantage of the first sensor, the optically pumped magnetometer, is that it is a scalar magnetometer, so we do not need to measure the orientation of the sensor because it measures a scalar quantity. So for analyzing the OPM data, we only need the current recording. But for analyzing the SHFT data of the vector magnetometer, we also need attitude information. So the Euler angles, the orientation of the sensor in the Earth coordinate system. And to measure these angles, we use inertial measurement units. We have used different units throughout the last years, and I will come back later to this topic. Yes. So let's start with the first case. The first case I want to present is a survey performed by the University of Münster in Namibia at a known mineral deposit, the Hope deposit. The surveys were performed in 2021 and 2023, and we use both the scalar magnetometer and the vector magnetometer. And the advantage of using both receivers is that they are sensitive in different frequency ranges. So the scalar magnetometer is sensitive between 1 and 128 Hertz, but the vector magnetometer is sensitive between 32 and 1000 Hertz. So they are basically complementary. And if we, let's try the pointer. If we look at the noise spectra, for instance, we see the black curve is the scalar magnetometer, and the vector magnetometer are the orange or blue curves in the 2 different versions, with a rod or with a rope. And we have kind of a small range where both sensors overlap in sensitivity, but if we think about lower frequencies or higher frequencies, they are complementary. So basically we can increase our subsurface or the resolution of our subsurface investigation by combining the 2 data sets of the sensors. And this is what we do in all 3 surveys I will present now. And another advantage of increasing the data coverage is if we use multiple transmitters for the same flight area. So for instance, this is the 2021 flight area, and we have 4 transmitters, and we cover the same area with multiple transmitters. So we increase our data density, and with that we decrease our model uncertainties in the inversion process. I will not go too much into the details of the inversion methodology today because I want to focus on the results. So here you can see the 3D inversion result of the combined data sets. In total, we used more than 100,000 data points in the inversion with 260,000 model parameters, which is quite a huge inverse problem. And with our Gauss-Newton inversion algorithms and our tools custom and PyGimli we use for inversion, we end up in 7 iterations with a very good overall misfit convergence. and inversion result, which you can see on the right. The inversion mesh we use is discretized, so we have like a fine discretized subsurface volume below our survey area, below the transmitters and the receivers. We can adjust the cell sizes, and every single cell is an inversion parameter which can have a unique resistivity value in the inversion process. And here we have basically identified the main target, which was already known, the hope conductor, but also two further structures. And to have a better look about the conductors at depth, we can look at slices through the model. So here you can see the slices P3 to P23. On the left, it's a little bit small, I think, the scales, but basically if we start from west to east, we have like the hope conductor here at the surface, dipping down towards greater depths, which we can see here in the following slices. And in the center of our investigation area, the conductor splits somehow in two arms, which is also confirmed by other measurements performed by TerraTech Namibia. And we have also a small conductive structure here. So this is our 3D inversion result. And if we compare it to a sketch of the hope conductor, which is where the location is known by drillings. So the hope conductor is in the center, and they have drilled a lot here to follow the dip of a conductor. And if we compare it with our inversion result, we see that it matches quite nicely with the dip and the true depth of the conductor. So this is a very nice investigation result, which will be published soon, hopefully, with a kind of double publication by Philip and me in geophysics. And I want to comment on the advantage of combining both data sets. So on the right, we can see the shape of the conductor, which we would get if we only use the vector magnetometer data in blue. So we would see a shallower conductor. And if we only use the scalar magnetometer data set, so basically the lower frequencies, we get like the green shape. And if we combine the two data sets, we end up with a red shape, which matches quite well to the whole ore body. But a single data set would not have been able to resolve the conductor so well. So it is definitely of advantage to combine the two data sets to decrease the equivalence in our modeling results. And this is basically the key message, that it is really helpful to have the two sensors with the UAV system to get kind of, more reliable inversion results. And this can be also confirmed quantitatively. I don't want to go too much into detail, but it's possible to calculate so-called resolution kernels, which is kind of a measure of the model resolution for specific model cells. We could do it for all 250,000 cells. Here we picked only 3 in different depths. And if we think about cells in 200, 400, or 600 meter depth, we can see that the resolution of the inversion result is quantitatively improved if we combine the data set, because the resolution kernels are higher. And last slide on this case, I want to also give a short overview how we are able to validate our inversion results and the quality of our inversion results. So one measure, of course, is the overall chi-square misfit. So here we start with a chi-square misfit of 160 for the scalar vector magnetometer, 60 for the scalar magnetometer, and 120 for the combined approach. And we always end up after 6 to 7 iterations with a value of 1.4, which is a very nice convergence. But this is only a global measure, and this does not respect if we have like individual outliers and things like that. So if we want to really look into detail, we can go to view the misfits line by line. Here on the right, you can see a comparison of the data and the final responses
of the MAC error data for one of the profiles, P9, and the transmitter one. And what we compare is kind of the data with the error bars shown in blue. And then we have the final response on the individual MAC error inversion result and of the combined inversion results. And they look very, very similar. So this shows that the two model responses are kind of, they allow kind of equivalent subsurface models because the misfits shown in orange and green have basically the same range. So there are no outliers or there is no systematic trend visible. This is a nice indication that the approach works quite well. And we could also, I mean, we would need to study like hundreds of these figures to view all the data in the end. And Said developed with Thomas an approach to analyze our misfits more statistically for certain components, for certain frequencies, which will be part of another publication next year. I don't want to go into detail here. Next survey was already presented 1 year ago in the House Colloquium, so I will keep it short. We have done a similar investigation comparable to HOPE in Spain at the Poderosa mine. Here we were able to measure 3 transmitters in one big flight area with 6 subpatches. The survey was performed together with the University of Münster in 2022, and again we used both sensors, the MAC error and the SHFT. And the difference, the big difference to the Namibia case is that we have steep topography here with height undulations up to 300 meters. So if we operate our UAV, we need to take care that we keep line of sight. So basically we need to stand on top of the mountains to have like an overview of the area when we fly with the UAV, which is a kind of challenge in this particular area. And we also need to avoid flying too deep into valleys because then we cannot see the UAV anymore. So this is kind of the first survey performed in such a challenging environment. And we are quite happy that we could collect data. And the final inversion result here shows also a number of conductors which are very well aligned with the regional geological strike direction. And in particular, this conductor is placed exactly where we have drilled the Poderosa deposit. So again, we found the conductor we expected and a number of further conductors, but it is not possible to validate these structures because it's kind of the first result. So there is no reference data available. I'm not sure if a local company will use these data in future for their exploration goals, but again, we found the structures we expected, and here we could even identify targets down to 800 meter depth quite reliably because the overall subsurface resistive is lower compared to the Namibia case. Another survey was performed last year with the University of Cologne in Bavaria at the Kropfmühl graphite deposit. There is also a history because before we performed in the framework of a DESMIX project, helicopter SAEM-based measurements with 7 transmitters in a bigger region, which were, the results were published by Wiebke Mörbe in 2024. And now we focus in the west of the deposit. So here's the active mine. And in the west of the mine, there is a known occurrence of a graphite. And in order to validate the UAV-based SAEM method, we performed a small survey in this region. In more detail, we have installed again 4 transmitters with overlapping flight areas. So similar procedure as in HOPE and Poderosa. And in addition, we have, or the University of Cologne has performed many ground recordings with electric and magnetic fields. So here the methodological approach is to compare the UAV-based results and the inversion results with results obtained from a ground-based survey only. To have like, a comparison, what is the advantage of of measuring the data in the air and measuring data on the ground. One big advantage, of course, is we collected the airborne data set in 1 week, and I think the ground survey took 2.5 weeks or something. And here we have like maybe 200 receiver locations, and airborne we have thousands of receiver locations. So we can definitely collect more data in a shorter amount of time using our UAVs. And nevertheless, e-field information at the surface are also valuable because the e-fields are kind of sensitive to structures at the shallow surface and provide additional information in the inversion process. And Wiebke is currently working on a publication combining inversion results based on the ground-based survey only, based on the vector magnetometer data, which actually show a graphite-related conductor, which is already known from helicopter airborne measurements quite well. And she's also combining the ground-based with the UAV-based data in inversion and analyzes quantitatively the resolution capabilities of all the different data sets. So this is a current work in progress on this case. But key message again is we found the target we expected at the location where it was expected. Now let's jump to another application. This survey was performed in the framework of a Blue Transition project last year, also in the Münstedt area. So this is the North Sea coast. Here we have Bremen, here is Münstedt. And the idea here is to identify the salt freshwater interface and depths between 20 and 200 meters in this region, because we know from existing data that we have saltwater intrusions in this area. Again, we have a survey with 4 transmitters with an overlapping flight area. I think it became quite obvious that this is kind of our ideal setup to increase the data coverage, or if there are issues with one data set for one transmitter, we can still cover the area in the inversion. So it's basically unavoidable to use multiple transmitters in the same region if you want to get good inversion results. And here we have also another methodological aspect. The problem is that our inertial measurement unit was attached to our ADU data acquisition system, but our ADU stopped working. So we used the backup from the University of Münster, but where we couldn't use the IMU anymore. So we switched to the iPhone to measure the attitudes as an alternative. We have experimented with this also in Tropfmühl, and the iPhone was also a backup in Namibia. So I will comment on this later on in the discussion. Problem is, if we do not have IMU data, we cannot use our vector magnetometer data. So we need to find a way to get the correct Euler angles and the orientation of the sensor. And we have 2 days of data with good IMU data available, but for the other 2 transmitters, we do not have these IMU data. We only have the iPhone data. But in contrast to previous surveys, the iPhone data shows systematics, or the data processed with the iPhone Euler angles show systematic errors based on flying back and forth, which is definitely not good. So we cannot use these data, basically. And Philip has developed a machine learning-based processing algorithm to kind of train an algorithm with the IMU data and with the attitude information of the UAV to predict our Euler angles for other data where we do not have the IMU. So this is, oh, what is here? What happened here? I have no idea what happened in the center. Okay. Well, artifact. So basically in the center, we should have the iPhone image. But with the machine learning algorithm, we can kind of rescue our data where we do not have IMU information, which is pretty nice for this survey, because With that, we can also use the TX2 and the TX4 data and combine all 4 transmitter data sets in the final inversion result. And I do not want to go too much into detail here because Barbara and Eva will present this topic in the next house colloquium in 1 week, but only a small teaser. For instance, we can compare our semi-airborne electromagnetic results here on 2 profiles with a SkyTEM survey, which has, of course, another scale because SkyTEM is a helicopter-based system. And it's a stitched 1D inversion approach, if I'm not mistaken, which we compare against our 3D inversion approach. So it is quite natural that we have kind of sharper vertical resistivity contrast in the 1D inversion approach compared to our 3D results. But the lateral heterogeneities can be better resolved with a 3D inversion approach in principle. And for instance, we can see in this area a drop of the salt freshwater interface quite nicely, and this matches also well with the SkyTEM results. So in principle, this is also a nice validation of our method because it's the first time we applied the UAV-based SAEM surveying for a groundwater application. And last case is in the framework of the geometer project. I will not show too many data here, but I want to mention the survey itself. So the geometer project is a big project where LIAG and Uni Münster and Uni Freiberg and other players are involved to develop advanced characterization strategies for waste disposals. And the aim is to use different magnetic and semi-airborne EM methods from the air and to also 3D seismic surveys at the ground and combine this and validate this with boreholes and borehole data analysis, both borehole geophysics and core data analysis. And this project is complete work in progress, but last year we have performed already a helicopter-borne survey, which led to a preliminary inversion result, and we have also performed a UAV-based survey in this area. And the UAV-based survey focuses on this specific region, and the aim is to see if we can add more details to the inversion results of the helicopter-borne data, if we also include the UAV-based data on the local scale. And later on, if the data are available, hopefully in some time, the idea is also to constrain our EM inversion with geometrical information we have obtained from the 3D seismics. And again, we have a potential here to apply also the machine learning-based attitude correction algorithm, because we had also some issues with the IMU in the survey. And yeah, I already mentioned the idea is to kind of improve the inversion by adding structural constraints. So let's discuss our results briefly, or our experience is. In general, it works. Otherwise, we would not have obtained so many data and inversion results. But the process of data acquisition and processing and things can be sometimes frustrating, because with our system, we encountered often data logger restarts during the flights. So basically, our data acquisition stopped and we needed to repeat flights or couldn't continue at all, or needed to use a backup system. We thank the University of Münster in this context for supplying us with their ADU to continue the service in Kopfmühl and Minstedt. That was really great. I've talked a lot about IMU issues, so we have used different IMUs from different suppliers, Xsense, SBG. We have a UAV internal IMU data we have used in iPhone. And the only IMU that performed robustly is an IMU from IMA, installed in that second version of the University of Münster, which is towed by the rope in 10-meter distance. And this is the unit we want to bet on also in the future. Of course, we have a payload limitation, so it's not easy to modify the system a lot. We always need to try to have like lightweight components if we want to improve the system.
And other aspects are, for instance, also mechanical abrasion. We have like 3D printer parts, which kind of start to not break apart, but which need to be replaced after some time of serving. We have also the connections of the rods with screws, which become loose, and when we have more torsion and when we get more systematic errors in the orientation of the sensor and things like that. So these are all aspects that need maintenance of the system, but it's doable. It's challenging, but it's doable. During surveying, of course, we need to consider that we always need to have line of sight, which is also difficult if we fly far away in a kilometer distance. It's not so easy to see the UAV anymore. It's possible, but it's not so easy. And with topography or forest, it becomes more difficult. If we plan in rough terrain with topography, we need to take care that the UAV does not crash with trees or anything. We have problems with feed because the batteries kind of blow up, and they don't blow up, but they increase their size, and dust is not good for the system and for the rotors. And if there is too much wind or rain, we cannot fly. So these are the environmental conditions. And of course, in the dry areas such as Spain, we also need to really think about where we can place our transmitters to have an appropriate grounding, because otherwise we would not get strong source signals. Considering the processing, I already mentioned the attempts to optimize the roll, pitch, and yaw corrections based on the IMU data we have available. The machine learning-based approach is existing, but I think it can be further developed, and it is quite promising also for future applications. And considering the inversion, we can do the inversion of these sizes of data sets right now, but larger data sets would become pretty difficult with the current approach, because the direct calculation of the explicit calculation of sensitivities with a direct solver requires lots of memory. And this is kind of the bottleneck at a certain problem size. And to overcome this, we want to use strategies based on iterative solvers. There's a work by our colleague Raphael, submitted to GOD last year. And this is also work in progress to kind of reduce the RAM requirements, and also being able to run inversions maybe on smaller computation platforms and not our big workstations. And in the long term, it would be also good. So in each case, we have applied different measures to analyze the inversion quality, to calculate resolution statistics or misfit statistics. And we want to combine all these things now in a kind of common workflow that can be used for any new case, kind of summarize the knowledge gained by our working group. Major conclusions. Yes, we have 3 successful demonstrations of the method to explore known mineral targets. We have a first successful application on groundwater characterization. And we developed open access inversion tools, which can be used also for the inversion of other large-scale 3D EM datasets. The comprehensive analysis of the inversion results is possible, but of course we need to kind of develop the workflows that it is all part of something a kind of non-developer user can use to invert the results. And personal opinion, I think the experiences we gained during the last years with the surveying, with all the challenges, the technical issues, are very valuable to continue with further developing this method. And with that, one outlook is to develop a new receiver system. I talked a lot about technical issues and limitations. So last year, a new SHFT sensor became available, which is more sensitive towards lower frequencies. That means towards higher penetration depths, which is kind of fitting what we want. And we have also a new data logger available, which is more lightweight than the old version, the ADU11. So it's not yet available, but very, very soon we have already a prototype for testing. And Münster already has it, but we also want to use the U200 IMU in a new bird, which is currently developed in the next months, to have like also a rope-towed receiver system to improve our data quality and the robustness of our data collection. And this bird will hopefully be applied in a new project, which started mid of last year. It's called SIG Aqua, dealing with groundwater exploration in Namibia and Zambia. And here we work together with the VGR and TerraTech and the University of Namibia and Zambia and the SADC Groundwater Management Institute in Africa. And the idea is to characterize aquifer boundaries and their vertical separation, as well as salt-freshwater interfaces, and find out more about saltwater intrusion in the pilot regions with our geophysical approach, and combine this with geochemical and hydrogeological investigation methods and samplings to end up with a local hydrogeological model combining the regional groundwater conception with our geochemical analysis in the survey region and our survey results of UAV-based SAEM surveys. And with that, I talked about it, a new system should be developed. Of course, we want to continue keeping our tools accessible and usable for the community. And in that project, we also want to establish a new network, because in this region, I think LIAG was not active so far, at least not in the context of groundwater exploration. So it's nice to have a BGR as a cooperation partner here in this project to start something new. And with that, I want to thank you for your attention.